3 o'clock. Welcome back to your favorite class. The best hour of your day. Rawr. Dynamics time. Hopefully you got your homework in. Let's do it today on impact and momentum. A lot of questions on it in office hours. Hopefully we got that sort of figured out. All right, it's going to be a question on impact and momentum or something of the like on the next test. So hopefully you're solid on that sort of stuff. That means we start new stuff today. And the new things that we're going to talk about today is a new analysis method for linkages. And there's a new slide deck that's posted. Okay. Just a reminder too, the simulation is also due next Tuesday, and that is on work and energy. All right, forgot to make that announcement. Okay, new topic. That new topic is an old topic, which is linkages. Are you confused yet? Good. I hope you're confused. All right, comments. Nope, meeting has started. So let's get you over to the writing pad. This was a student submitted meme. I appreciated the meme, except there's one error. Can anybody find the error in our student submitted meme? Do dee 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 dee. It ain't squared. Yeah, it's foot per second squared. But the general feeling is good. I like what they did with the meme. It's especially pertinent for like problem number 1 in the last homework, so I thought it was kind of funny. All right, enough of that. Let's do some dynamics. I hope you wore your math pants today. Today's the mathy day. If not, I'll give you a minute to go put them on if you need to put on your math pants. All right, you got them on? Let's go, baby. New topic, linkages. And while it is a new topic, it's actually an old topic because you've seen linkages already in this class, though we hadn't really like given them this formal name. So let's look at what a linkage actually looks like. All right, here's the linkage. Bang. I will title it a linkage. So it's this series of individual links that's kind of contained in a two-dimensional plane, right? Of links in a 2D or quasi 2D plane. It's not actually in a 2D plane, but it's more or less like kind of contained in a two-dimensional plane. And I'll write that you've seen this before. All right, and the topic to come is velocity and acceleration analysis. Oh, spelling is hard. ANALYSIS of linkages. So you're going to say, Dr. Hart, we already did analysis of linkages for velocity and acceleration, and you're right. Back in week 2, we did analysis of things that looked a lot like linkages. So if you remember back in like week number 2, real week number 2, not quarantine week, but back in week number 2, we had this example problem. We had this general problem where we were given omega AB, theta, and told to solve for like the velocity of point D. And this is something that we worked through. And you did this analysis with traditional kinematics, right? You used, or we together used things like the velocity at A is the velocity at B plus omega AB cross the position vector, which locates A from B, ... and same thing for the acceleration. You had those kinematic equations, right? You generally use those kinematic relationships. And that's fine when the number of links in the chain is relatively low. So in this particular example, you only have 2 links, right? Link number 1 and link number 2. So when the number of links is small, this kinematic analysis that we do is fine. Okay, it gets the job done. It's a little cumbersome because you got to like propagate information, and it's annoying in some respects, but it's okay. So with low number of links. Kinematics is fine. Here is fine. So using those general equations is okay. But remember, it gets more annoying as we have more and more links. So let's show you an example of that by recalling a homework problem that you did. This is homework number 2, problem number 3. So you had seen a linkage before with homework 2, problem number 3, and this was your general problem statement. Shown below is a 4-bar linkage. This is not a typo. This is a 4-bar linkage, and I'll explain what that means in just a little bit more. You're going to say like, oh, it only has 3 connecting links. Okay, yeah, that's true, but the general definition here is a 4-bar linkage, and I'll explain that in just a second. That's not a typo. And I write in this homework problem from homework number 2, we will discuss linkages like this in greater depth later in the class. That time is now. Okay, we're going to be discussing these in greater depth right now. So like the next week or so, we'll talk about these in a little bit more depth. If you recall back, this homework problem is annoying. Okay, you've got to figure out all the angular velocities and all the velocities of all the pins, and then you can use that information to figure out like accelerations and propagate all that to all the different lengths. God damn, that's annoying. All right. So I even kind of make the note here, this problem is hard, and if you can make it through, you're very ready for exam 1. Okay, so those of you that did it and did well, good job. You probably did well in exam 1. Well, all of you did it well in exam 1, but some more than others. The basic idea is that, okay, we're starting to get pretty annoyed with this like 3-link setup. Once we start going to 4, 5, 6, 7 links, I ain't doing that old method anymore. All right, I'm old. I ain't doing that anymore. There has to be a better way that we can do this, and there is, and that's what we're going to talk about over the next week. So, is there a better way? A better way. Yes. But we need to use complex math. And complex has two meanings in this particular situation. Complex meaning it's complicated, and complex also meaning that it involves complex numbers. So if you've seen complex numbers in the past, I asked the other class, I was going to ask the other class, and I forgot. How many of you have seen complex numbers before? Like have used it in your math classes? Do you use it in like your calc classes? Can I just like get a yes or no, or maybe don't remember? I've never seen it before. Like where do you see it? Like which calculus level? Or is it in like your DiffyQ class? We use an EE201. All right, and in linear networks. In my dreams, Alec invented complex numbers. All right. So you saw it in linear networks. All right, that's a good start. So that's good. High school, says Caleb. Damn, what high school did you go to? Genius High School? God damn. He must have went to high school in Canada or something. Or no, is that Jared? I think that's Jared. Who lives in Canada. Okay, whatever. Anyway, a stupid one, says Caleb. Incorrect. You're a very bright young man, Caleb. Don't put yourself down. Is there a better way? Yes, but we need to use complex numbers. So let's refresh ourselves on complex numbers, and then let's dive in on how we might use complex numbers to represent positions, velocities, accelerations. Did you do that in 201? Probably not. I don't think you like represent like position vectors and velocities in 201. I don't think so. Okay. Enough jibber jabber. Let's go. All right. So, complex numbers, a brief review by yours truly, Dr. Hart. So complex numbers use what's known as the complex unit. And that is square root of -1. In this class, and probably in your electrical engineering networks classes, you used the variable j to represent this. Sometimes you'll see it as I, sometimes you'll see it as J. I will use J because your textbook uses J. So what are you going to do? The complex unit J is the square root of -1. With that, then a complex number is a real number multiplied by J. That is not a complex number. Sorry, an imaginary number. Is real number multiplied by J. An example might be something like x equals 5 times J. That would mean that x squared is -25. All right, this gives us a way to represent square roots and squares using some negative numbers that otherwise we wouldn't be able to like take the roots of. All right. With that, then, a complex number is a combination of a real and an imaginary number added together. All right. An example might be something like x is 10 plus 5j. So then if I take x squared, I use my FOIL method, and I'll get something like 100 plus 50j plus 50j minus 25. It's my FOIL method. Or you'll get something like x squared is 75 plus 100j. Right? So again, algebra is kind of proceeding as normal, but we'll note that something like j times j is -1, and I've kind of represented that here by leaving off what is like the j squared term on this right-hand side, and instead substituting this negative sign here instead. But we all sort of get the general idea. All right, so this is complex numbers, and complex numbers can be represented in what's known as the complex plane. So complex numbers can be represented in the complex plane. Right? And the analogy here is that you're used to a plane that contains like the x direction and the y direction, but the complex plane has the real axis as the x-axis and the imaginary axis as the y-axis. So it's analogous to xy plane with the real and imaginary axes, replacing x and y axes. So in your mind, that should look like, here you have the real axis, here you have the imaginary axis, taking the place of the x and the y axes. We can use this complex plane to represent complex numbers. So say we have an example here. That is, some complex number is, let's say 2 plus 3j. Right? So we have 2 that's the real value and 3 that's the imaginary value. So here we have like 1, 2, and 1, 2, 3. So we have here this location, which is 2 in the real direction plus 3 in the imaginary direction. 2 plus 3j. How does this relate to dynamics? How does this relate to rigid bodies? How does this relate to linkages? Well, if we could use this same idea to represent position vectors in real space, using a general idea of like a complex number representing a position vector, we might be on our way. So here we have 2 plus 3j, but if we thought of this as kind of like a vector locating this particular spot, then we might be able to do something slick by using complex numbers to sort of manipulate position, velocity, acceleration, so on and so forth. Okay, so this is a vector locating 2 plus 3j. And this here is what's known as the complex plane. You have this real x-axis and imaginary y-axis. When we're talking about a two-dimensional space or this like vector notation, then we have to be able to describe unit vectors in the various directions. And this just comes down to mathematically what's known as basis vectors, or some unit that defines where we are in this particular vector space. So in complex plane, is vector algebra an elective that you guys can take in your math, like for math courses? Is there like a vector analysis class? I think there is, isn't there? Anyone taking that right now?
It's one of the level 300 math or sciences you can take.
Okay. Do you guys talk about basis vectors in that class? No. Okay. I'm going to go with no. All right. Well, let's just say that, all right, you haven't yet. Maybe you didn't at all. All right. So in the complex plane, your basis vectors, which are the spaces that represent where you can possibly live, would be something like in the real space, the basis is 1, and in the imaginary space, the basis is j. So what do I mean by that? All right. It will help to think about the Cartesian equivalent. In Cartesian, basis vectors are I and j. Okay? They're kind of like unit vectors. Okay, so think of these maybe as like unit vectors. They're not technically unit vectors, but they behave like unit vectors. All right, so the space that we could move through is the space that is 1 multiplied by any actual number in like this real space, and j multiplied by any real number in like the imaginary space. That's what we mean by these are the two values that make up the basis for all other vectors in that space. All right. So if you want to represent some real value, it's 1 times something. If you want to represent some imaginary number, it's j times something. And those are the two basis vectors that make up that like two-dimensional space. That's what we mean by that general idea. Okay. So considering that idea, you could represent a vector in complex space with a complex number. Where 1 and j are like I and j. All right, so I'll just say that and then I'll demonstrate that in just a second what I actually mean. One last thing that I need to talk about for complex numbers is an identity that exists that relates exponential function to some of the trigonometric functions that you might be familiar with in your Cartesian space. And I don't really have time to derive this. This equation has got a lot of history. But I'll say one last thing we need. Is Euler's formula. If you take anything away from lecture today, take away Euler's formula, okay? It is like majestically amazing. You can read books written on Euler's formula. It's insane. And Euler's formula is this. It relates, here I go, right in the eyes. J theta. I learned imaginary numbers with little I, so I tend to like write little I instead of little j. E to j theta is cosine theta plus j sine theta. This is Euler's formula. There's also a negative equivalent, which you can see with trig identities. And also that is that e to the negative j theta is cosine theta minus j sine theta. We'll see this applicability in just a hot second. right? You might often see this represented as e to the plus or minus j theta equals cosine theta plus or minus j sine theta. And this is how I have it represented in the notes. You probably talked about that one in your electrical engineering class if you did complex numbers. All right, but this is actually like two equations, one with the plus, one with the minus. If you take anything away from lecture today, please take Euler's formula. All right, now math precursors done. Let's talk about how we might actually use this complex notation to represent these position vectors. Right? So here we are in our traditional XY space. And let's say that you have a position vector that exists in this space that defines like some point out in space that is here. And let's call this position vector capital R. Right? Let's say that capital R is at some angle with the horizontal, which is theta. And we know that we can split that vector up into components along like I and j, where let's say that this length here is Rx, and this length here is Ry, right? So in your traditional definition of what this position vector is, you could write this position vector R is simply Rx I hat plus Ry j hat, right? If magnitude is capital R bar, you could also represent it as magnitude of R times cosine theta I hat plus magnitude of R sine theta j hat. Everyone should be comfortable with this. No one should be squirming in their chairs right now. You're the smartest person in your chair. Stop squirming around, right? As long as no one else is touching your chair, you're the smartest person in your chair, right? So there, R is the magnitude of R cosine theta I plus the magnitude of R sine theta j. That's your traditional representation of what this is. Now, if we want to represent this in the complex plane, we can basically just eliminate what is this x-axis and what is this y-axis and re-represent them as like the real axis and the imaginary axis, where the unit vector defining the real axis is the value 1, and the unit vector defining the imaginary axis is the value j. So that's your traditional representation. We also have your complex representation, which is like R is equal to what would be Rx plus j Ry. This is your real component. This is your imaginary component, right? So we have like a unit vector times this Rx, which is 1, which is hanging out there. That is the real unit vector, 1. I'm not including it here because it's obvious, right? Times the imaginary portion, Ry and the j. This could also be represented as the magnitude of R times what is cosine theta, the real portion, plus j sine theta, the imaginary portion. Yes? And we just saw that this whole guy here is represented with Euler's formula, e to the j theta. So we can represent this position vector in the complex space as the position vector R is the magnitude of this position vector R times e to the j theta. And this is where we begin our long, arduous journey. How are we doing on that? Everyone's head exploded yet? Now, why would I want to represent my position vector in the complex plane? What is the benefit? Well, the benefit is if we're trying to take the derivative of the position to get the velocity, the derivative of an exponential is freaking easy, okay? It is just the coefficient leading the derived value, all right? So in this particular situation, it's going to be something like if we're taking the derivative with respect to theta, it'll be Rj e to the j theta. It's freaking easy. A caveman can do it, all right? So this is why it's beneficial for us to do position, velocity, and acceleration analysis in this complex plane, because we have all these exponentials where the derivatives are incredibly simple. right? So benefit, derivatives are easy. Not like spelling. Spelling is hard. Okay, so an example, if I wanted to take the derivative of this with respect to theta, the derivative of the position vector with respect to theta is simply the magnitude of this vector times j times e to the j theta. Right? That was easy. I just pulled the j out front. Fine. All right. Now, when we're talking about velocities, here's with respect to theta, I took the derivative. If we want to take the derivative with respect to time, we're going to have something like the derivative of the position vector with respect to time, which we know to be the velocity, is the derivative of the position vector with respect to theta times the derivative of theta with respect to time. Recall that this is the chain rule. So we just wrote what this dr d theta is. Okay, that is here. All right, let's do this with a color. Colors are cool. Yeah, color. All right, dr d theta, that is here. And d theta dt, we typically just note this as theta dot. Or when we're talking about dynamics, we write this as the magnitude of omega. All right, so now we've got like the derivative of our position vector with things that we can understand. The magnitude of the angular velocity and this derivative of the position with respect to theta. So ultimately, what we're going to end up with is something like the magnitude of r times theta dot times j e to the j theta. And this is a common expression that you might see for the velocity of a particular piece with a known angular velocity theta dot and magnitude of position vector r and location of that particular piece, just theta. It's like touching or bordering on the idea of polar coordinates here, right? Not quite polar coordinates, we're in the complex plane. This here is a vector representation. Right? It has magnitude. Here is your magnitude. And it has direction. Direction is associated with this particular portion of the equation, right? So here, magnitude. And the direction is embedded in these bits. So this is a vector notation. It doesn't have little I or little j like you're used to with your Cartesian coordinates, but that's the general idea there. All right. So this is how we're going to use complex notation to move forward, right? It will take a little getting used to, I bet, sort of writing vectors in this way, not representing them with your traditional IJK components, and that's fine. One last note I want to make about this complex vector notation is that we really only have use for this notation when we're in 2D. And that's because the real axis takes the place of the x-axis, the imaginary takes place of the y, and we don't really have anything to take place of z. Okay, so we can only really work in 2D here. All right, so we've kind of like hinted at or touched at what the velocity is going to be. Now let's actually dig in real deep and look at what this velocity analysis is going to be. And let's motivate this with an example that we saw in like week 2 of the notes. And that is this like crank example. And it goes back to like the example that I showed at the very beginning. So say we have this sort of link in a linkage and we know something about its angular velocity, we know something about its position, and we want to find what is the velocity of the end of this link at point B. So have the position vector r, or what I'll relabel as the position vector r locating B from A. And we also have, let's say that we know the angle theta, which we do here is this 40 degrees. And we also have the angular velocity of AB is negative omega AB in the k hat. Or we'll say, with this idea in mind, that theta dot is negative omega AB. This is the magnitude of the angular velocity, theta dot. All right, it's what we're going to use in our velocity analysis for this particular example. So let's get on with it. Let's represent the position vector which locates B from A. If you're going to do this in traditional Cartesian coordinates, you'd have something like, well, let's define the magnitude first. Here, let's represent the magnitude of the position vector of R arriving at B from A as capital R, which we know is 3 inches in this particular example. It's given to us. And in Cartesian, we have like the position vector locating B from A is R times cosine theta I hat plus sine theta j hat, obviously. Right? In complex form, you can say that this R arriving at B from A is the magnitude multiplied by the direction, e to the I theta. And I wrote I again because I'm a dumb head. All right, j theta, j. Okay, don't be using I. It's like burned into my brain to use I. That's how I learned complex numbers. Got to use j. All right, r e to the j theta. And this is just, again, leveraging like that Eulerian representation. Right? So let's look at what the velocity is. Oh, excuse me. It's the derivative of the position vector of B from A with respect to time. We showed with the chain rule before that this is the position vector locating B from A with respect to theta times the derivative of theta with respect to time. Right? So here the derivative of the position vector with respect to theta, that's easy. So here this is r j to the e j theta times the derivative of theta with respect to time is theta dot. All right, so easy a caveman can do it. All right, so this is a vector representation of our velocity. Obviously. Now, it's hard to interpret physically what that is unless you've been working with complex numbers for a very, very long time. But let's whittle this down a little bit and maybe we can see physically how this might be represented. All right. So let's put Euler's formula back in. All right. I forgot my theta. I'm bringing the theta dot out front here. And so here we're going to have something like r j theta dot times my Eulerian representation, cosine theta plus j sine theta. I can distribute the j here and here, obviously. When I do this j times this j, it's going to be j squared, which will be -1. Frankly. And then velocity of B relative to A is r theta dot. I distribute the j in, and I'm left with what will be negative sine theta plus j cosine theta. All right. Now let's take a step back and look at this guy here. Here's my magnitude. it looks a lot like r omega. We know that this is the case. The magnitude of the velocity is r times omega. So this is very similar to what we might expect. And here we have like what is like the x direction, because this is the real component. And here, this is the imaginary component, which is like the y direction. Okay, so we're representing the x and the y directions appropriately with real and imaginary directions. Right? So let's recall our definition for theta dot. Here we had this negative direction for omega, so negative omega AB. And then we're going to have that the velocity b with respect to a is going to be r omega, times I just flipped the sign on these guys. This will be sine theta minus j cosine theta. All right. So this is your complex representation of the velocity at b relative to a. Right. This is a vector form. In the complex plane. If you want to go back to Cartesian, that's fine if you're more comfortable. R omega AB multiplied by sine theta I hat minus cosine theta j hat. You're just replacing the unit vector, which is like 1 with I hat and j with j hat. All right, so this is your representation in Cartesian. So we see here we have some positive component in I hat and some negative component in j hat. Same thing that we see in the complex plane. Some positive component in the real direction, some negative component in the imaginary direction. So if we go back up to our figure, is that what we have? Yes. We have some positive component of this guy in the real direction, and we have some negative component of this guy in the imaginary direction. All right, so we see that coming through with our analysis here. All right, so let's finish this off now and look at the acceleration as well. And the acceleration is going to proceed in a very similar manner. All right. We're going to motivate and use the same general example. And let's recall that the velocity of b with respect to a, in the most basic of Eulerian terms, we wrote all the way up here as rj theta dot e to the j theta. All right, so that's what I'm going to capitalize on, or that's where I'm going to kind of start with. So here the velocity of b with respect to a is rj theta e to the j theta. I'm going to rearrange this slightly by putting the theta dot at the end. You'll see why in just a second. This is rj e to the j theta times theta dot. All right, we're going to take the derivative of this with respect to time. The acceleration of b relative to a. If we do that, the acceleration of b relative to a is equal to the derivative with respect to time of rj e to the j theta times theta dot with respect to time. All right, so let's do this. We'll use the product rule in this particular situation. So where we have, this is like u, and this is like v, and then the product rule is u v prime plus v u prime. This is supposed to be a v. All right, so remember your product rule. So we're going to have here something like the time derivative of this first piece is going to be, pull all the constants out front, JR e to the j theta. So I'm pulling all that out, and we're taking the derivative of the second guy first. So we'll take the derivative of this now, pull all that first stuff out. So this is like u times the derivative of v. So this will be d theta dot dt plus the derivative of the first times the second. So this will be the derivative of the first bit, which is j r e to the j theta with respect to time times the second theta dot. All right, let's look at one of these in a little bit more detail. So this guy here, this is theta double dot, which is analogous to like the magnitude of the angular acceleration alpha. Right. This guy here is a little bit confuddled, but we had seen this before. And this guy is just going to be what will be j r times j e to the j theta times theta dot. Complicated. All right, so I had to bring the j down here for the derivative, and I also had to carry through this theta dot that comes from d theta dt in the chain rule. All right, so now we're ready to sort of rearrange some of this. And we'll have the acceleration of point B relative to A is this first bit, which is j r theta double dot e to the j theta, plus the second bit now here, which I just showed, was jr times j e to the j theta times theta dot, all times, don't forget this theta dot over here, theta dot. See here that we have like a j times j, and we have two theta dots. So we'll simplify this slightly, and we'll have the acceleration of B relative to A is j r theta double dot e to the j theta minus r theta dot squared e to the j theta. This is your most general expression for the acceleration of any arbitrary point given this position vector that you know. Now, this looks foreign, okay? But this is a vector. And if you look, if you squint hard enough, squint your little eyeballs, squint them real tight, you can see some stuff. This looks a lot like R alpha cross R, right? So here this is like theta double dot times R, let's say, has a magnitude of R. So this is your tangential component of acceleration. If you squint your eyes real hard, this comes from omega cross R, which is something like theta dot times R, right? Squint your little eyeballs, and that's what you'll see. Right? This is centripetal component. Right. So there we go. These are like the magnitudes. Here's a magnitude, here's a magnitude. And your direction is contained in like this and this, as well as this. All right, there's where your direction is contained. All right, so that's your complex notation. We can expand with Euler's formula. And remember Euler's formula, e to the I theta is cosine theta plus I sine theta. We're going to plug that in here. Again, I'm saying I, but I mean J. You know what I mean. Or do you know what J mean? No, you know what I mean. Okay. Oh, that was a good one. Do you know what J mean? Oh, that's funny. I got to do something here. I'm going crazy. All right. Let's plug in Euler's formula. Away we go. R theta double dot times J, that will remain. Cosine theta plus J sine theta. Now here I am over here. This guy will also retain minus R theta dot squared times cosine theta plus J sine theta. Now I want to get all my real and imaginary components together because all the real components are like what's representing the x direction, and all the imaginary components are like what's representing the y direction. So let's combine real and imaginary terms, and you'll be left with the following. All right, so you've got to like distribute this j in here. So this will be an imaginary term after distributing the j. This will be a real term after distributing the j because we're going to have j times j. This guy will be a real term, and this guy will be an imaginary term. We all cool on that? We all capiche on that? So the final result is that the acceleration of b relative to a is going to be, here I have this j times sine theta, so we'll have a negative r theta double dot sine theta. Then this real component here is minus r theta dot squared cosine theta. This is in the real direction. And then I'm adding to that what is in the imaginary direction. This is going to be from the tangential term, r theta double dot cosine theta. And then the imaginary term over here, I'll have a minus r theta dot squared times sine theta. Ooh, baby. Oh, and this is all times j. So here's your like x direction. And here's your imaginary. So this is a complex vector notation representation of the acceleration of point B relative to A for the crank that we showed above. Complicated. Damn. Hope you put your math pants on. And we see flavors here. Again, I'll remind you the flavors. It's like Baskin Robbins. There's so many flavors, 31 flavors. Here, this R double dot term rears its head. This is like your alpha cross R. That's where this comes from. And then you've got this guy. This is like your R theta dot. This is like your omega cross R here. All right. Dang. So we're going to use this complex notation to simplify things, believe it or not. I know you don't believe me right now, but I promise it will be more simple when we use this notation going forward with multiple links. Okay. So that's it for today. Thank you for coming. Hopefully you stayed awake and I didn't blow you away with all this complex notation. This is giving me PTSD to linear algebra. The girl with the pokey teeth. Thanks, Caleb. It's not that disgusting. Where's the other term? What other term? Oh, this is a relative acceleration. So remember that the general equation for the acceleration is something like, you want the acceleration of b is the translational term plus this term. Yes? Is this what you're asking about, Alec? So this is all the fixed axis rotation term here. This is your translational term, which still might possibly exist. This is your fixed axis rotation. That's why we have here the acceleration of B relative to A. Understand that, Alec? Got that? Does he have it? He does. All right, good. Rachel Cole, 3 o'clock on the homework. Well done. I knew I could count on you.